everybody. So first of all, I have to tell you that my lecture will be very different from the lecture we just heard. So I'm an experimentalist, so we are very proud because we just managed to repair the projector and now we have red here. But it also means that I will try to talk about as many experiments as possible. It will not always be possible because some of the situations I will talk about, there are no experiments yet. But as soon as possible, so if there's something, I will talk about the experiments. And also I have to say that in my case, the viscosity is absolutely not one. On the contrary, the viscosity is one of the things that we will mainly be concerned to find out how the viscosity might look like and on what the viscosity will depend. So in general, we will change our point of view a little bit for what I will be talking about. So I will be talking about suspensions, and I've showed some examples here. I think a lot of these things we have already touched on in other talks. So the first example is an example of red blood cells. So all of these examples are more or less microscopic objects. They will constitute a suspension of particles. So in this case, it's red blood cells which have a strange shape and can be deformable. Here, this is the paper pulp. So I think we saw some of this in Mike's talk, where you see fibers. They will later on form paper. And this is E. coli microswimmers that we have already seen in Kenny Breuer's talk. So most of the things we've heard up to now were concerned with individual particles, with the interaction of individual particles with flow, how these particles perturb the flow around them, and how the flow deforms these particles. So what I will mainly try to do is to understand if I put these particles mostly in a simple liquid, so how will the presence of these particles change the macroscopic flow properties of their suspensions. So we want to link the microscopic perturbation of the flow due to the particles to the macroscopic change in flow properties. This also means that we have to go back and understand what are the macroscopic flow properties. So macroscopic flow properties, we have already mentioned things like the viscosity, but maybe there are other properties. So there are simple fluids, there are complex fluids. So before I go really into detail on the suspension properties, I will take a step back and to tell you about Newtonian and non-Newtonian fluids, and also a little bit about rheology. What are the technologies to characterize macroscopic fluid flow for classical rheometers, but also for more recent rheometers that have been developed recently, which are microfluidic rheometers. So if possible, I will do this today, but I've seen with all of the others that normally one doesn't get as far as one wants to, so we will see. And then in the following lectures, what I will do is I will talk about suspension formed by these type of particles that we have all individually already seen. Simple spheres, fibers, flexible fibers, and also microswimmers. So as I said, I will try to link the perturbation that these particles induce when they are under shear or under flow on the flow to the macroscopic properties. And most of the time I will try to do this in relatively dilute situations where actually the perturbation by the individual particle can be directly linked to the macroscopic properties. But I will also go to systems that are a little bit more concentrated where we have interaction between particles, and we will see how this changes properties. But as I said, before going there, we have to step back a little bit and have to discuss what are macroscopic properties and what are the definitions of these properties. So I will really go a step back and tell you first about the definition of the Newton viscosity, as Newton has introduced it quite a long time ago. So I will try to write on the right position of the board. So actually, what did Newton do? So Newton defined the So this is the shear viscosity. And he actually did this in Principia, and I forgot the year, but it's really long time ago. So his basic idea was that you put a fluid between two plates, you translate the upper plate, you apply a certain force, and you look at the velocity of the upper plate. And if you have a Newtonian fluid, if you double the force, you will double the velocity. So basically, that's his definition of the viscosity. So if I write this down for you, you have an upper plate and a lower plate. You apply a force to the plate, it will slide at a certain velocity. If you do this you will create a velocity profile, which is also a velocity profile that we have seen already a lot of times, which is a simple shear. So I can also put like an x-axis and a y-axis here, and I will have a velocity in the x direction that will only depend on y. So of course we all know that the velocity does not directly link the viscosity does not directly link the force and the velocity, but it relates something which is a stress. So which is actually, if you say this is the surface, so the stress is a force per surface, and it doesn't really link the velocity, because if I change the distance in the gap between the two plates, actually it will become more difficult to slide if the gap is smaller. So this is called the shear rate, which is actually the derivation of the viscosity of y, or in the simple situation is just the velocity divided by the gap width. So this gives us the definition of the Newtonian viscosity, that actually the shear stress is the viscosity times the shear rate. So this is Newton's viscosity. And the viscosity in this case is a constant. Okay, but of course, I mean, we've done low Reynolds number flows now for 3 days. We have seen that flow situations are normally much more complicated than this very simple situation. So if one wants really to understand what goes on, one has to generalize these relationships to a tensor notation where I can describe actually flows in all directions. And that's what I will do next. So I think I will have to write smaller. So I will do not a lot, but just actually go from this very simple notation to the tensor notation, and we have seen all of this already. And what I want to develop is something like a generalized Newton's law. Yeah, I know this is in the shadow, but so for this we will use a stress tensor. So I actually call the stress tensor sigma EG, and sometimes if I just want to use the tensor notation, I use this, and I will try to make the nice notation that Howard introduced, that this is a tensor if there's two bars. So what is the stress tensors? We have already seen this quite often also. So if you think that you have a certain plane somewhere in your space, and it is oriented in a certain direction, so I have different components of the stress tensor. So actually, I can have a component which is parallel to the normal, which is sigma xx, and then I have shear components, which I should maybe draw like this, sigma xy, and one here is sigma epsilon. So I can have normal components, which is sigma xx in this way, and I have shear components, sigma yz and sigma zx. And if I write this down, I can say that in general, sigma xx is a normal stress. And sigma yx and sigma zx are shear stresses. So we've already seen this already. If I know the stress tensor, I can calculate the force on any surface in a flow. So this is the force per surface. And this can be just written in index notation like sigma EG in G. So we've seen all of this already. It's just rewritten in my notation. So what is the stress tensor? So actually the stress tensor has two components. It has the component that comes from the pressure and the component that comes from the viscous stresses. So here we are interested in the viscous stresses. So we will look at the viscous stress tensor. So we've already seen this also. So you have the component from the pressure. And so this part here is the viscous stress tensor. So I will not always use the prime here, but all of the following I will discuss the viscous stress tensor, because that's where the microscopic properties, the flow properties go in. So the next thing we want to do is, of course, we want to link the stress tensor to the shear in the fluid. So we've introduced this already also. So what we need is the rate of strain tensor. So EYG or E, as you have already seen. So this one is constructed on the velocity gradients. So the tensor of velocity gradients, GIG, is just the derivative. So now you will see all the things you've already seen in index notation to change. But we also know that now we're interested in viscous friction, and viscous friction only happens if you have actually sliding of different layers in the fluid. So if you have a solid body rotation, it will not influence the viscous response. So we will separate this into a symmetric and into an antisymmetric part. So the antisymmetric part the antisymmetric part will correspond to a solid body rotation, and the symmetric part will correspond to the shear. So this part is typically called omega, and then now we are interested, or you can have it as small omega EG if you want, and this is the tensor. And then the symmetric part, which I call EIG or E, is just by construction d VI over d xj plus dVg over dxi. And in Howard's notation, this was 1/2 V plus transpose. Okay, so far we've really kind of done nothing, and we just rewrote everything in tensor notation. So we now have a viscous stress tensor, and now we have the shear tensor. So the only thing we will do now is we will link both of them, and that will give the generalized Newton's law, which is nothing else than the constitutive equation. So the constitutive equation I will write down is only valid for incompressible fluids. So just make this as a remark. So this is kind of a side remark, so I get the constitutive equation. So the constitutive equation will just be sigma Eg equals 2 eta E by J. actually the 2 only comes from the definition of the 1/2 in front of the shear rate tensor. So we have already seen this constitutive equation, and so far we took it for granted. However, we will start talking about non-Newtonian fluids, and if you have non-Newtonian fluids, this constitutive equation does not look like this or even does not exist. So we have to be careful now to be sure if we have this constitutive equation and if we can use it or not. So just a second remark. So the Stokes equation or the Navier-Stokes equation in the form that we have seen so far is only valid if I have this constitutive equation. So just these small remarks. So back to Navier-Stokes or just to Stokes. So there was the notation where actually things had been written. If you write things in terms of the stress tensor, sorry, if you write actually your notation in terms of the stress tensor, you're fine, because this relation holds always. But if you replace this by the other form of writing that this becomes the viscosity and the velocity, this is only valid if you have this constitutive equation. So be careful when you deal with non-Newtonian fluids not to start from this version of the Stokes equation and try to replace the viscosity by something strange here. If you have a dependence of the viscosity on the shear rate or something like this, you have to start from a formulation where you actually have the stress tensor in there and not already the viscosity. Okay, so with this, we have set the basis for the explanation what is a Newtonian fluid. So a Newtonian fluid is something that verifies this constitutive equation. A Newtonian fluid only has one parameter to describe its flow. It's the viscosity, and this viscosity is a constant. So for a Newtonian fluid, we know everything. As soon as you know the stress tensor, you know the shear. If you know the shear, you know the stress tensor. We have the Stokes equation. We can solve, well, more or less whatever we want. However, what happens if I now go to complex fluids? So now let's go to complex fluids. Before going there, another remark on what is a Newtonian fluid. So actually in a Newtonian fluid, like a typical example is water or oil of a relatively low viscosity. There's no internal time scale. So it actually means that typically it's fluids of a molecular structure. So it's the molecular structure is of the size of nanometers. So a time scale for thermal fluctuations or something like that is extremely small. So it can be like 10 to the minus 9 seconds or something like that. So it means if you apply a shear rate to a fluid like this, you will not be able to change the structure of your fluid. So your fluid is unchanged by external flow. So there's no internal time scale that can interact with the flow you apply. So this is why the viscosity is a constant and why you deal with a Newtonian fluid. So in a simple fluid, you have a molecular structure which can be, I don't know, from 10 to minus nanometers, 1 to 10 nanometers. And this means if you have typical time scales, they will be of the order, for example, of 10 of minus 9 seconds, so very small. So what this implies is that the flow does not change the structure of your fluid. So the structure of the fluid is unchanged by flow. So now if we go to typical non-Newtonian fluids, so we have touched on non-Newtonian fluids already a little bit during the previous talks. So for example, polymer solutions. or all the things I want to talk about in the future, fiber suspensions, active suspensions. So in all of these cases, you add mesoscopic particles or mesoscopic structures to the fluid. So as those structures are quite big compared to the molecular scale, so depending on what we are looking at, if we go from the polymer, which can be, I don't know, 100 nanometers, to the microsperma, which is 10 micrometers, you can even have bubbles or things that are even bigger. That means that in this case, typical time scales, which can be time scales for vertexation, for deformation, for rearrangement, for orientation, will become much bigger. So these time scales will become comparable to the typical time scales of the flow that you apply. So the flow that you apply can change the structure of your fluid. And in this case, you will have a non-Newtonian fluid, where you have a feedback, so the flow will change the structure of the fluid, and the changing in the structure of the fluid will feed back on your microscopic flow properties. So that's what is called a non-Newtonian fluid. Okay, so non-Newtonian fluids. So you have mesoscopic structure. So typical, maybe, I don't know, from 100 nanometers to maybe 100 micrometers. And this can be polymers. Can you read anything if I write down there? No? No. Okay. So I'll try to stop here. So there can be polymers, fibers, bubbles, whatsoever. And in this case, the characteristic time scales, as I said, are bigger. So the characteristic time scales can be from 10 to the minus 3 up to 100 seconds. So this is very approximative. And in this case, the structure of the fluid is changed by the flow. So you get a new organization. And you get a feedback. So this will make things nonlinear. So if for the moment I only talk about viscosity, this will typically mean that the viscosity will depend on the shear rate. So for example, the definition for the viscosity will mean so for example, this is the non-Newtonian viscosity. But actually, it's not the only non-Newtonian property that you can observe in complex fluids. So it's not only the viscosity can be changed, but there are also other properties that can occur in the fluid. And before going in more detail, I wanted to show you a number of small films that are actually mostly from the lab of Gareth McKinley at the MIT, who works a lot with complex fluids. And that will show you quite amazing properties, mainly of polymer solutions here. So imagine you take a fluid, and in most of these cases, you put a not too high amount of very flexible polymers into it, and this is what you can observe. So here you will see that you can actually fill a syringe that is not in contact with the fluid anymore. So he puts the syringe in the fluid, and you see there's no contact anymore, and he still manages to fill up the syringe with the polymer solution. So this actually comes from a strong resistance of the polymer solution to stretching. So there's flexible polymers in there that don't want to be stretched, and they stabilize this filament very strongly. A similar effect can be seen here. where they actually roll a fluid around something, and you see they will empty the beaker. So this really looks like something elastic. And it's again the resistance to stretching of the polymers that stabilizes the flow here. Yeah, then at the end they will break down. Which is certainly much more than just having a viscosity that depends on shear rate. Another example, which is actually very well known, and I think most of you have already seen this, if you, for example, beat egg white, if you have a rod and you turn the rod in a polymer solution, so normally the fluid should be pushed down by centrifugal forces, but in this case it will go up. And this is what is called an effect of normal stresses. So in this case, it's again flexible polymers that are stretched along the streamlines, and as the streamlines form a closed circle here, it's like a pressure that will push fluid inwards and the fluid will move up there. Another effect that you might already have seen, so you can see this, for example, if you have shampoo under your shower and you press it very hard, and when the shampoo comes out, it will actually, like you see here, not decrease the diameter, but increase the diameter once it comes out of the nozzle. So this is called dye swell, and is also an effect of normal stresses, so additional tension in the direction of the streamlines. And then I will just finish with viscosity that depends on the shear rate. So actually there's a very nice demonstration of this in one of the films that you can find on fluid mechanics on the internet side of the MIT, but I actually don't know how to copy the YouTube videos to have a good film, so you have it. Okay, Babette has it, so for my next talk I will have it. So just to tell you, this is an effect of the viscosity that depends on shear rate, and what is done here is that the first experiment you have sedimentation of two spheres in water and a polymer solution, and in the first situation the shear rate is very small because the beads fall very slowly, and in this case the viscosity is identical. However, when you open the reservoir, actually you see that the polymer will flow much faster, because in this case you create a higher shear rate, and the polymer solution, which is in this case typically a rigid polymer, not a flexible polymer, will shear things, so the viscosity goes down and the reservoir will empty itself much quicker. Okay, so you see, yeah?
No, just a comment. It seems that in most of the situation you showed us, there is a local anisotropy of the viscosity.
So yeah, so normal stress is an anisotropic effect.
Yes. So in that definition, there is no.
No, I'm not finished yet. So actually, what I here, this is just the first non-Newtonian property you can imagine, is that the viscosity depends on the shear rate. This is what is shown here. I have not talked at all about normal stresses yet, nor about elongation of viscosities. So this will come in a second. It was just to get you interested into the topic. And something that I should also say that I didn't clearly state is, so we've seen that there's for all non-Newtonian fluids, there's an internal time scale. So it's very important to know about these internal time scales, and actually non-Newtonian defects will only occur if your shear flow is strong enough to overcome the inverse of the internal time scale. So I will write this down for you. So this is called a Weissenberg number, and only if this Weissenberg number is large enough, you will have non-Newtonian effects. So for non-Newtonian fluids, there's always an internal time scale. So there's maybe one exception that we discussed last time, but I will come back to the shear thinning fluid a bit later. Okay, so to formalize these things, let me go on somewhere on my notes. Maybe here. So let me just write the comment on the time scale down, because this is really important. So note, for non-Newtonian fluids, there is always an internal time scale. So this is something like a relaxation time. And I will call this relaxation time lambda. And the non-Newtonian effects will become only important when your shear rate is larger, so then the inverse of this time scale. This means that actually the Weisenberg number, which is defined as the shear rate times the relaxation time, is larger than 1. So this means that the object that you put in the flow does not have time to relax. So does it really feel the flow? If it relaxes too quickly, it will not feel the effect of the flow. Okay, so if we go on, so all the film that I just showed you, and it has been pointed out, so it's absolutely not enough only to take non-Newtonian viscosity into account. We might have much more actually properties of the fluid that we have to take into account. But before going there, we have to realize that now we don't have a constitutive equation. So actually our life is much more complicated than before. That also means that it's more difficult to characterize the flow, because we don't actually know how many parameters we will need to characterize a flow. So what people did that do rheology is actually that they tried to make their life a little bit more easy. So they do what they call, they define rheological flows. So they say, okay, these fluids are very complicated. I don't really know what to expect. I will only test them in defined flows, because these flows have certain symmetries. And if I use the symmetries of these flows, I can make some assumptions on my stress tensor. So this will make my life much easier. So typically this is a simple shear flow and a simple elongation of flows. And strictly speaking, only in these flows you can define the material parameters that you will measure. Okay, so this means here, so we do not, in most of the cases, we do not have a constitutive equation. Actually, it's the thing that we all are looking for. So for all of these complex fluids, what we would like to have is to have a constitutive equation. And if possible, we would like to actually match or derive this constitutive equation from the microscopic properties. But it's not possible, or not yet possible, for all of the complex fluids that we work with. So we have no constitutive equation. So what we do is we define rheological flows. So actually we do this because then we have less parameters to define. Okay, and that's what I will do now. So we have seen all of these flows already over the last days. So typical rheological flows. So it's first of all the simple shear flow. We've already seen this quite often, so the simple shear flow looks like this. The velocity in this case can be written as the shear rate y0, 0. And in this case, of course, writing the tensor E or the stress tensor is really very, very simple. And they look like this. So you only have the diagonal element. So luckily it turns out that it's really symmetric as we have imposed. So it's not the diagonal element, huh? It's these two shear components. And if I have this, and if now I'm in a situation of a Newtonian fluid, I can directly write my stress tensor. Which will just give eta gamma dot 0, eta gamma dot 0, 0. So there's absolutely no surprise here. That's exactly what we would expect, and that's what we have seen so far. So writing this down is mainly interesting to see what changes if we go to non-Newtonian fluids. So the second type of very simple flow is simple elongation. So the example that we have seen in the previous talks was the stagnation point flow. Okay, where fluid comes up from above and goes out on the side, so it's compressed here and it's stretched here. So in this case, the velocity can be written as the extension rate and x. So in the previous talks, this had been written in 2D. So there was x here and minus y here. So I will write it in 3D. So as we need mass conservation, I will just have a 1/2 epsilon dot y and minus 1/2 epsilon dot z here. Okay. So we'll just play the same game. I will write the shear rate tensor E. So it just gives epsilon dot 1/2 epsilon dot, and I have a minus here and a minus there. So you already see that the symmetry of the flow is very different in this case. And in this case, one defines what is called an elongational viscosity. So I will write the stress tensor first, which actually looks as 2 times. So the small e means elongation, epsilon dot minus eta e, epsilon dot minus eta e, epsilon dot, and all the rest is zeros. Yeah, not sure. So I mean, remember, this is still a Newtonian fluid. So I told you there's only one constant. And now I'm telling you that this is the elongation of viscosity. So we will see how this relates to the shear viscosity. So the definition of the elongation of viscosity is actually eta E equals sigma xx minus sigma zz divided by epsilon dot. And actually it turns out that this is just 3 times eta s for the shear viscosity. So it's purely geometrical. It's still the same fluid, it's still the same viscosity. It's just that I look at extension and not at shear. So it's actually the same that for people who do determine elastic modulus, like the shear modulus and the Young modulus, you always have a factor 3 in there. Yeah?
Is this also sometimes called extensional?
Yes, yes. Maybe it's always called extension viscosity? Okay. So I think this is kind of a translation. Okay, before I go on, I want to make a comment of something that has, I mean, I think kind of implicitly or explicitly already been stated quite a lot over the last few days.
It's just minor. I think what you mean in the sigma equation is you just mean eta S, because that's the stress in the fluid. And then your A to E is 3 A to S. I think over here you mean A to S.
Oh, yeah, okay. I agree. Actually, yeah, I think it should be like this. Yes, of course. Sorry. Yes, you're right. Of course. Absolutely. So how it is absolutely right that, of course, here it's the same viscosity because the link from E to sigma was just done using the constitutive equation. And it's only the definition of the extension of viscosity which actually gives the 3 times eta s, which directly comes out of this if you write this correctly. Okay?
How do you call epsilon dot?
The extension rate. Which, yeah, I can define it in detail later. Yeah.
And incompressibility is always...
Yes, everything will be incompressible for me. So a remark that I wanted to make. So we have, I think, implicitly or explicitly already seen this quite a lot over the last days. Simple shear is not at all a simple flow. So simple shear is a combination of a rotation and an elongation, and actually this elongation, 10 minutes? Okay. And this elongation is actually oriented at 45 degrees. Okay. So this, if you find this, just if you write the separation into omega and E. So this is the rotation given by omega. This is E. And what you also, well, if it were still there, you could see that actually E, in the way we write this, is not diagonal. So it means that the axes of the extension are not in the direction of the axis of our coordinate system. So the extension is in this direction. And that's also why we have sigma xy and sigma yx in the stress tensor. And that will also be something that is quite important when we will go back and discuss how different particles will behave in different flows.
I think you need to rotate that about another 7 degrees.
Okay, I'll try this later on. It's a sketch. Okay, but I will try at last to come to the definition of the non-Newtonian properties, because that's what all this was about. So why did I do all these definitions? It's because actually we wanted to look at non-Newtonian fluids. So now if I look at the non-Newtonian fluids in these flows, yes, in the rheological flows, so if we are in simple shear, so by symmetry arguments, it can be shown that the only components in the stress tensor that are not zero are sigma xx, sigma xy, this is 0, sigma, well, xy or yx as you like, it's symmetric, sigma yy 0, 0, 0, sigma z. Okay? So now with these, you can construct a number of things you can really measure in experiments. So first of all, of course, we have the shear viscosity. So sigma xy is nothing else than the viscosity times the shear rate. But don't forget, the viscosity can now depend on shear rate. And now the anisotropy comes in, because now we can have anisotropic terms on these lines, and this is the normal stress differences. And these normal stress differences caused, for example, the rod climbing that we just saw. So N1 is sigma xx minus sigma yy. N2 is sigma yy minus sigma zz. Okay. You only measure differences because if you had isotropic pressure, for example, it doesn't contribute to the movement. And in simple elongation, actually, formally things don't change a lot. So sigma remains unchanged, but now the elongation and viscosity, so it's still defined as sigma xx minus sigma zz divided by epsilon dot, but it can be much larger than 3 times the shear viscosity. So the relation that we had before, that the extension viscosity and the shear viscosity were only related by a factor 3, does not hold anymore. Okay. So this was the introduction to the main non-Newtonian properties that we have already encountered a bit over the last days, but this is how they are defined. And in summary, what you should keep in mind is that the stress tensor now is nonlinear. There's dependencies on, of all of these properties on the shear rate, and it becomes anisotropic. So let me just write this down. So as a summary, so the stress tensor becomes anisotropic this is what gives rise to the normal stress differences and non-linear. For example, eta depends on gamma dot. Now we have more than one constant to describe a material. And what else did I want to say? Okay, and strictly speaking, these constants are only defined in rheological flows. So I still have a little bit of time to talk about rheometers. Okay. So, well, now we have defined these properties, but now we also need to find out how we can measure these properties. So in a classical way, all of this is done using classical rheometers. So if you go back to the idea of the definition of the Newtonian viscosity, so actually the idea was to have a simple shear flow, to have like something like where the upper plane is sliding, and you create a simple shear flow. This is something that is very unpractical to do in a laboratory. So what the rheometer typically does is that actually it has a geometry that turns. So here are just some geometries from typical rheometers that I have represented. And I would say the main are like plate-plate geometries, where you have a button plate that does not move, and an upper plate that is actually mobile, that comes to a certain distance and then will rotate. And the thing that is the closest to the situation where you have a plane that slides over another one is the so-called quad geometry, where you have a cylinder that will turn inside of another cylinder. And if you go to the limit where the radius is big and the gap between the inner cylinder and the outer cylinder is small, you're very close to a situation where you actually have a simple shear flow between two planes. And actually these geometries are shown here too. And just some words to what do you really measure. So how you do rheology. So first, this is the part where we do classical rheology. Oh yeah, sorry. So what you typically do is that you use a rheometer, you have things that turn, and what you need to do is that you have a certain rotation rate, and you have to convert your rotation rate in a shear rate, and then you will measure the couple on your geometry, which I call the torque, which is C, and this has to be related to the stress. So rheometers can either impose the rotation rate and measure the torque, or can impose the torque and measure the rotation rate. So both of them exist. And this link is typically done by the geometry. And I will just write this down for you for the quad geometry. As an example. So the quad geometry is an inner cylinder and an outer cylinder. And the inner cylinder will turn with a certain rotation rate. And we will go to the limit where the gap is small, which is called a small gap approximation. So this means that the two radii, well, strictly speaking, go to infinity, and the definition and the difference between the two radii, which is often called d, will be very small between the two radii. And in this case, I'm really in the limit of the two plates. And in this case, actually, done very easily. So the shear rate, remember, in a simple shear flow is nothing else than the viscosity divided by the distance between the two plates. And this is omega times r divided by the distance between the two plates. And then the next thing we need is to link the torque to the stress. So how do you do this? So the torque is something like a force times the distance on which you apply the force. So the force, if I want to recover it from the stress, is the stress times the surface. And the surface in this case is the inner cylinder. So it's sigma times 2 pi r, and I still have an r from here left. And then I also have to think about this dimension and add the length of the cylinder, which is L. And then I put all of this together and use my definition for the viscosity, and you find that the viscosity is something like the torque times the small gap and the omega are 3 to pi L. So it's not really necessary to know this formula in detail, but it's important to know that to do measurements on a conventional rheometer, you have to link the shear rate to the rotation rate and the stress to the torque, and you do this via the geometry of your rheometer. I will just point out the next very important geometry, which is this one, without doing any calculations on this, which is the cone plate. And I have the impression that I need to stop. So the cone plate is also a geometry where you can have a constant shear rate, because one of the advantages, the big advantage of the quad geometry, is that the shear rate is constant. You're in the situation of a simple shear, so even if you have non-Newtonian fluids, you don't need to worry about what happens with them, because there's only one shear rate imposed in there. And actually the same happens for the cone plate geometry, because in this case, well, it's not a very nice drawing. You have actually a cone which is cut very slightly here and which is above a plate. So if this cone rotates, what you can see is that actually the rotation rate increases with the radius, but the distance between the two plates also increases with the radius. So the shear rate remains constant. Just write this for you. The shear rate is something like omega r, and the gap is something like r and the tangents of an angle phi here. And very often this is just, well, I'm not sure where I should write this. Can just be written as omega divided by this angle. Okay, so this is also a geometry where you just have a constant shear rate. So it's actually a very nice and very convenient geometry. I will make one last remark. Yeah, sorry.
So it measured the same thing? I mean,
Yes. Yes. So what I did.
Convenient, is it?
Sorry?
So it's
Oh.
convenient to use the cone plate geometry because
The two geometries that I just introduced have the advantage that they have a constant shear rate. There are other types of geometries. So if you would not have a cone here but a plate, then your shear rate is not constant. And as we know that non-Newtonian fluids interact with the shear rate, this makes your measurement more ambiguous. So if possible, if you can work in a geometry with a constant shear rate, it's much better. So it's two very different ways of introducing this. So one remark, what might be limiting about these geometries is actually that you're limited in the torque you can measure. So if you go to fluids that have a very small viscosity, or if you want to go to very small shear rates, you might be limited by the torque of the rheometer. So typically making rheological measurements of systems that are very close to the viscosity of water, or where you expect very small non-Newtonian effects, or if you want to look at small shear rates, the resolution of your apparatus will not be sufficient. And a lot of the suspension properties that we want to discuss in the following actually are exactly limited, actually placed in this range. So the conventional rheometers are not always the best rheometers. And that's why we'll talk a bit more about microfluidic rheometers tomorrow. I think there was another question. Yeah.
Question about depending of the rotation velocity, if you think the shear rate will stay constant.
Mm-hmm.
This means if you have a higher Reynolds number of rotating from some regime, you have broken vortices.
Mm-hmm. Yeah, okay.
So
mm-hmm.
you don't have exactly this.
Yes, so I agree. So one of the other limits of all of these geometries is that you have to be very careful to stay in the small Reynolds number regime. So if you go to higher Reynolds numbers, there's what is called Taylor quad vortices, which are very beautiful, but which are not at all what you want to measure. And what you see typically on your measurements, so it's quite easy to detect. So if you measure viscosity as a function of shear rate, so you will have very strange things in the beginning. This is a problem of the resolution of your apparatus. Then you have nice measurements, and then suddenly viscosity will go up. And that is typically does not necessarily mean that you have shear thickening or something like that. It can often mean that just that you go to Reynolds number which is too high. Okay, I'm done, or have more time? I'm done. Okay.